So let's do a couple of examples. Some of these examples or some of these problems are easier than the others. They all involve the energy equation, but it's easier, much easier if with the givens you can find the Reynolds number. Things are much simpler. If you need velocity or d, which appear in the Reynolds number, then things are going to be harder. So let's start with an easier one where we know enough information to calculate the Reynolds number. So what we have is a repeating water pipeline, 1,000 meters between pump stations, and we want to find the required pump size, and we're given a pumps are 75% efficient. So we're going to want to do the energy equation, so let's go ahead and write that down. And we're going to then want to cancel some terms, but we have P1 over rho g plus V1 squared over 2g plus Z1 equals P2 over rho g plus V2 squared over 2g plus Z2 plus HS plus HF. All right, so this is water, so our new value, which happens to be mu over rho, is 1.005 e to the minus 6 meters squared per second. Okay. Our pipe is 6 centimeters in diameter, and the distance between pumps is 1,000 meters. Okay, so the first thing you got to do in all these energy equation type of problems is make an inlet and an exit. So we got to figure out where we're going to put one and where we're going to put two, and what we always want to do is try to make it as simple as possible and still give us the information we need. So since we're trying to find our pump size, we probably want to include a pump in our calculation. The other thing we want to do is look and see, can we find a place to put our inlet and our exit so that some of the stuff is going to cancel out? Anywhere we put our inlet or exit, the velocities are going to cancel out, so that's a good thing. Also, our elevations, our z's, are going to cancel out. But if we put one here and two here, our pressures are also going to be the same. Okay, so they'll also cancel out. So that's all good. So let's go ahead and cancel pressures. We said since the diameter's not changing, velocity's not changing. Since it's horizontal, z's not changing. So almost everything cancels out. So that's good. We do have a pump in between, so we're going to leave the HS in. And we are going to have flow through a pipe, so we're going to have frictional head losses. So just solving this equation, HS equals minus HF. And HS equals W dot over M dot G. This is on your equation sheet, as is HF equals FLV squared over 2DG, which is what we just found. Okay, so in order to get this F, what we're going to do is we're going to need Reynolds number. What we're solving for is this W dot S. Okay, so Reynolds number, VD over nu. Well, we need V for Reynolds number, but we don't have V. We've got Q, 135 gallons per minute. Well, Q will give us V, because we can say V equals Q over A. And if I go ahead and plug everything in, I'm not going to go through the math and unit conversions, but you get 3 meters per second doing that. Remember, you have to convert those gallons. All right, so then if I take that, plug it in here along with my diameter and my new value, I'm going to get a Reynolds number of 179,104, which is about 180,000. And it is turbulent because it's above 2,300. Which was our critical Reynolds number. Okay. Other thing we're going to need to find F is epsilon. Okay. Epsilon, this is you got to look at the material to figure out. It's a cast iron pipe. So table 6.1 has epsilons in it. For cast iron, you're going to get epsilon is about equal to 0.26 millimeters. Okay. And then our epsilon over D is going to be 0.26 millimeters. And our diameter is 6 centimeters, so that is 60 millimeters. So that comes out to be 0.0043. All right. So now, since we're able to find the Reynolds number, We've got a pretty easy case here. We can either plug Reynolds number into our equation for F or just look F up in the Moody chart. So let's look it up on the Moody chart. It's easier. Okay, so Reynolds number was 180,000. So 2 times 10 to the 5th is right here. 1 times 10 to the 5th here. Here's 1.5 times 10 to the 5th. So it is somewhere in this range. And we want to go up until we find the line where the 0.0043 for epsilon over d. 0.004, so it's going to be between 0.004 and 0.006, close to 0.004. So we're talking about right there. All right, and then we're going to follow that over to the left, and what I get is about 0.03 for F. All right, so 0.03 F, approximately 0.03 from Moody. Okay, other option would be to plug it into that equation, and that would be fine. You'd probably get something a little bit different, but remember these are only plus or minus 10% accurate anyways. So our HF is FLV squared over 2dg. We've got all that information. If I plug that in, I get 230 meters. Okay, so that's my HF, which also happened to equal negative my HS. So HS is minus 230 meters. And that was W dot S over M dot G. And M dot is rho Q, so W dot S over rho Q G, or W dot S over gamma Q. Okay, and gamma for metric 9790 newtons per meter cubed. So our W dot S is minus 19,000 watts once I plug everything in. But you have to remember, this is into the water. This is what is getting into the water. Okay, what work you're actually having to put into the pump, okay, has to do with that efficiency. So our efficiency of the pump equals power to the water over power into the pump. So electric power, mechanical power, okay, and so that's W dot S, and we'll call this W dot P for the real pump power. So our W dot P is actually going to be our W dot S over 7.75. So that's minus 19 kilowatts over 0.75, which is about 25.5 kilowatts. And there's your answer. Okay. These are very practical problems, by the way, something that you might have even done on co-op already, but it's very likely that you end up doing work like this out on real jobs. All right, so let's do one more example, one that's a little bit harder, and that is a case where Q is known, but D is not. So D appears in the Reynolds number. That's going to cause us some problems. Okay, so what we have here is this situation. We're pumping from one tank up to another tank. Cast iron again. This time we're doing English units. So epsilon is about 0.00085 feet. All right, so what we want to do is energy equation. You know, all these problems start with the energy equation. You'll have it memorized. P1 over rho G plus V1 squared over 2G plus Z1 equals P2 over rho G plus V2 squared over 2G plus Z2 plus HS plus HF. All right, for some reason, this is a picture out of the book. Ignore these 1s and 2s. I don't know why they put them there. We want to put our inlet and our exit where we know the most information. So where we know the most information here is at these free surfaces. And you always need to put one upstream of 2. All right. So let's put it at those free surfaces. The reason we want to put it at those free surfaces is, voila, using gauge pressure, P1 is equal to P2 and is equal to 0. Z1, or not Z1, V1 is 0 and V2 is 0. Let's make Z start here, which means Z1 is 0, Z2 is 120 feet. We do have a pump, so we need to leave an HS, and we are going to have frictional head losses in this little pipe. We're going to ignore them in the big tanks, but in the little pipe we will have frictional head losses. So one of the things we're given in this case is the pump power, and it's 80% efficient, which means our W dot S that actually gets into the water is only 80% of our power for the pump. Minus 100 horsepower. Remember, it's minus because it's a pump. Work going in times 0.8 minus 80 horsepower. Watch your units. Whenever you get in horsepower, that does not mean foot-pound per second. Those are not normal units. You're going to have to use a conversion to get out of that, kind of like gallons. All right, so let's calculate HS. W dot S over M dot G, which is, again, W dot S over gamma Q, minus 80 horsepower. I'm going to plug in the units, the numbers this time, just to go through those units. 62.4 is our gamma pound force per foot cubed. Our Q is 3 foot cubed per second given. Okay, so our feet cubed cancel. Okay, now we got horsepower times second over foot pound, or not foot pounds, pound force. Okay, so that is not a normal unit for HS. That's not going to give us feet. So what we need to do is look up our conversion, and it happens to be 550 foot-pounds per second is 1 horsepower. Okay, so the per seconds are going to cancel, pound force is going to cancel, horsepower cancels, and what we have is feet, which is good because these are heads. So heads always end up in length scales, length terms. Minus 235 feet. And that's our pump head. Not head loss, it's a pump head. It's increasing the pressure, which is why it's negative. So our HF then, back to the, rearranging this equation, HF equals minus Z2 minus HS. Well, that's going to equal minus 120 feet, and then minus a negative 235 is plus 235 feet, which gives us 115 feet. So that's our HF. What we're trying to find is diameter to use, okay? So diameter is in our HF, so that's good. So HF equals FLV squared over 2DG, all right? We're given a Q though. Let's put it in terms of Q. Since we don't know D, we can't just come up with a number for V, but we can just plug in V equals Q over A. So we plug in a Q over A where we see a V, and you get FLQ squared over A squared 2DG. And that is going to be 16 FLQ squared, because there's going to be a 4 squared in that pi over 4D squared. And then 2 pi squared D to the 5th G. Okay, so in that A squared you got a D squared squared, which is D to the 4th, and then you multiply it by this D to get that. And just simplifying that a little, 8FLQ squared over pi squared D to the 5th G. All right. Whew. And we are trying to find D. You would think that, okay, we can just solve for D, but there's a problem. And that problem is we got a D inside F too, right? F depends on D. Okay, if I just rearrange this equation, I know my HF is 115 feet, so right now I'm at 115 feet equals 8FLQ squared over pi squared D to the 5th G. If I rearrange that, I can get it down to, and plug in numbers, F over D to the 5th equals 0.254. 1 over feet to the 5th. Okay. Problem here, I have really still 2 unknowns. So what we need to do is figure out that F. And if it's laminar, it's just going to be 64 over Reynolds number, and we could use that fact, but most likely it's going to be turbulent here. So let's just go with the turbulent assumption. Assume turbulent. And at the end we need to check to make sure it really was turbulent. So F equals minus 1.8 log, and I can't use Moody this time because I don't have Reynolds number. Log 6.9 over Reynolds number plus epsilon over D over 3.7 to the 1.11 power, all to the minus 2 power. All right, now we can plug in for Reynolds number though. Reynolds number equals VD over nu. And we need to turn that into Q, so 4Q over nu pi D. Okay, and that's again because V equals Q over A. And combining, what I'm going to get is 0.254, 1 over feet to the fifth, equals 1 over D to the fifth, times this whole big mess, minus 1.8 log 6.9 nu pi D over 4Q plus epsilon over D over 3.7 to the 1.11 power to the negative 2. All right, big challenge. Solve that for D. Not so easy. So how do you solve this? Number of ways. The main way that I'm going to have you use is on your calculator. Use the solver on your calculator. You could also use MATLAB or MathCAD or GoalSeek on Excel, or trial and error. I'm not even going to write that because that's difficult. So basically try it on your calculator. See if you can learn how to use the solver. Most of you probably have a graphing calculator and can do it, and some of you in your scientific calculators can do it. So figure out how to do that. I'll go over it in class as well, but the answer I got was D equals 0.611 feet, which is 7.3 inches. Okay, so and then the last thing you want to check to see if turbulent. And if you do plug that in, you get a Reynolds number 577,000. So yeah, it's turbulent. So that's good. Try this yourself, see what you can do, and I will see you in class.